this once, almost 3 years ago, and I enjoyed it very much. Yeah, so today I'll talk about hydraulic fracturing by supercritical fluids and then consideration with microstructure in rocks. So before I start, I'd like to acknowledge my collaborators. So yeah, uh, I'm Keita Yoshioka, and then a lot of work that I present are actually done by my colleague at Leoben, Tao Yu. I think he's also online. And then also experimental works were done at the Tohoku University in Japan. Yeah, so let's move on. So yeah, so this is our motivation. So this is paper published in Geothermal Research Letters in 2017 by a group of people in Tohoku. So they have conducted hydraulic fracture experiment at 3 different temperatures. So this was meant to be for supercritical geothermal. So 200 degrees C and 360 degrees C and 450 degrees C on granite sample. So for low temperature, 200 degrees C, this is shown on the left. So the rock sample, the granite, is still in a brittle condition, and water is still below supercritical condition. And at this condition, they saw pattern of structure looks familiar to us, like bi-wing, a planar fracture pattern. And then as they increase the temperature, this pattern of fracture, morphology of the fracture looks more complex. So in the middle, it's 360 degrees C. So the granite, the brittle to ductile transition temperature for granite is around this temperature, 360 to 400 degrees C. So the rocks is transitioning to ductile, and also water is becoming supercritical as well. Then at 400 degrees C, at high temperature, so at this condition, water is supercritical and rock is ductile. And then we see very complex patterns of fracture. So they are small and also isolated, very complex patterns of fracture. So this paper was very interesting because in supercritical condition, supercritical geothermal systems, we thought that the rocks have very low permeability, and also it's very difficult to stimulate such rock because the rock is inductor. But their experiments show that well, looks like it's possible to stimulate to create the fractures even in supercritical geothermal conditions. But then question is why does the pattern of fracture change? Why do fractures become more complex as we increase the temperature? So then we can think of two reasons. So of course we know that the rheology of the rock changes, so it changes to ductile, and then also fluid rheology changes. So the water is already in a supercritical condition. So which contributes to the complex fracture. So then we have done experiment on PMMA sample. So we chose PMMA because it's a non-porous material, so that we can exclude the pore pressure effect, the fluid pressure effect. But also PMMA has a very low brittle to ductile transition temperature. So PMMA transitions to ductile condition between 80 to 100 degrees C. So and at that low temperature, water is still below supercritical condition. And we performed hydraulic fracture experiment on PMMA samples at those different temperatures from 20 degrees C to 120 degrees C. And at low temperature, so from 20 to 80 degrees C, we are able to create a fracture, a hydraulic fracture. But the higher temperature from 90 degrees C to 120 degrees C, we were not able to fracture the sample. So, we kept injecting pressure, just kept increasing, but there's no breakage. So from this experiment, well, at least we can conclude, well, we can suppose that the rheology of the rock or the rheology of the material at least did not contribute to complex fracture formation. So then that leads us to rheology of the fluid. So water being a supercritical condition, that might be the reason. And in their original paper of geophysical research letter, they actually mention this. So at low, well, at the supercritical condition of the water, viscosity is very low, and then fluid, the water can infiltrate into the sample, infiltrate into the rocks, and then that changes the effective stress, that reduces the effective stress. And then that reduction in effective stress might have contributed to this complex fracture generation. So then let's take a brief reminder of what effective stress is. Yeah, so effective stress. So the rock, the solid part of the rock is under this loading, and then the pore space, there's a fluid, and then there's a fluid pressure. And effective stress in this setting is defined as the total stress minus Biot coefficient times the pore pressure. And the definition of the Biot coefficient is defined as so. So it's this alpha m is the Biot coefficient, and it's 1 minus effective bulk modulus over solid bulk modulus. So the solid bulk modulus is this in this figure, this white part. It's a pure solid grain part of the bulk modulus, and then effective is this the average. So this the porous media considering the pore structure. So this effective, that's the effective bulk modulus. So for weak rock or high porosity rock, this effective bulk modulus is smaller or much smaller than solid grain part. So then in weak rock, this Biot coefficient approaches 1. And physically, that means that the fluid pressure has high impact on strain and stress. And on the other hand, hard rock or low porosity rock or very stiff rock, there's not so much difference between the effective bulk modulus and solid bulk modulus. And in this case, this term is close to 1. So then Biot coefficient also approaches 0. So then for low Biot coefficient, then fluid pressure has not doesn't have much impact on stress. Okay, so that's the brief refresher for what the effective stress is. So then if we look at the stiff rock like granite, and then there are some weak interfaces, maybe grain boundaries, or could be some natural fractures and so on. And when the rocks have such a structure or heterogeneity, we can also think that the Biot coefficients are also different. So at the weak interface, so in this image, this gray part or the white part, so the Biot coefficient should be close to 1 because effective bulk modulus should be very low compared to the solid bulk modulus. So the fluid pressure should have some high impact on the stress. On the other hand, at the intact part, this Biot coefficient should be close to 0 because this effective bulk modulus should be almost same as solid grain bulk modulus. So there should be some contrast in Biot coefficient for stiff rock with some weak interface. So then we consider this very simple settings. It's just a 1D bar, and we inject fluid from the left side. And then we also assume that there is some weak interface in the middle of this bar. Okay. And we consider that the Biot coefficient at this weak interface is 1. And then this intact part, the Biot coefficient is smaller than 1. Okay. So in this simple setting of this 1D bar, we can actually solve linear momentum equation analytically. So it's a 1D ordinary differential equation with non-homogeneous Biot coefficient. So Biot coefficient changes, except at this weak interface, the Biot coefficient is different. So that's the only tricky part, but we can solve it analytically. So this is how the analytical solution looks like. So the pressure profile, so we have an injection from the left. So at this point, pressure being the highest, and then pressure goes down to the end of this bar. And for the stress, so it is under the tension, and also it has some impact of this weak interface. So here the Biot coefficient is 1, and then in this case we said that the difference in the Biot coefficient is 0.4. So intact part of this rock has a Biot coefficient of 0.6. So then at the weak interface, we see that there's more impact from the fluid pressure, and then stress is being more tensile. But here, if the fracture were to happen, we expect that the fracture should be at the injection point, okay? Because this is where the the most tensile stress happens, okay? But interestingly, if we increase the difference in Biot coefficient, so in this case, difference in the Biot coefficient is 0.8, okay? So you can think of this as a more stiffer rocks, okay? Then, so this weak interface in this case carries more pressure effect, more tensile loading. And in this setting, the most tensile part becomes at this weak interface. And if fracture were to happen, then we would expect that the fracture will happen at remote location, not at injection point. And so we have looked at the Biot coefficient, but also fluid viscosity has impact. Okay, so of course, for hydraulic fracture to happen, the fluid pressure has to exceed the stress and then whatever the tensile strength the rock has. And if we have a low viscosity fluid, then the pressure drop is very small. Okay, so fluid can easily diffuse into the rock. So here the pressure profile is computed based on the water viscosity 1 E minus 3 Pascal second. But if we have a higher viscosity fluid, so it's 5 times higher viscosity, then again, this profile of the stress shifts again. And so this dashed line is the case where we have a higher viscosity. And in this case, we expect fracture to happen at the injection point. So this stress distribution, we see that it's impacted by both the fluid viscosity and the contrast in Biot's coefficient. So we can run a bunch of computations to see how the stress evolve with time with different Biot coefficient. And so we have run lots of computations and look at the stress at this injection point and also at this weak interface point. And we also found that, okay, if we scale the stress and time with this dimensionless numbers, we can actually, all the results actually converge into the same profile. So we can, using these dimensionless variables, we can collapse all the result into single figure. So this is what we have. So this is sort of the heat map of the stress. So on the x-axis, there's a difference in the Biot coefficient. So we change the difference in the Biot coefficient from 0 to 0.9. And then also these colors correspond to the stress. This is dimensionless stress. Okay, and then y-axis corresponds to the dimensionless time. Okay, so this is how the stress differences. I'm sorry, this is how the stress looks like. So at the injection point, for small difference in the Biot coefficient, the stress at the injection point is high. Okay, and we did the same things at the weak interface. And weak interface, for most of the cases, tensile stress is very small. So this blue region, tensile stress is very small. But if we increase the difference in the Biot coefficient, then tensile stress becomes bigger. Okay, and so you know, if we pick some fluid viscosity, and also if we pick some tensile strengths, we can draw a line. So for example, here we assume that the tensile strength of this material is 6.5 megapascal, and the fluid viscosity corresponds to the water viscosity at temperature of 200 degrees C. Then here we can draw a line at injection point, and then also at weak interface point. Okay, so what does it mean? So we can combine these two lines. So this black line is the stress, tensile stress corresponds to 6.5 megapascal at the injection point, x equals 0. And then this red line corresponds to the tensile stress of 6.5 megapascal at weak interface. Okay, and if the difference in the Biot coefficient is 0.6, okay, and then we start from here, and then as times goes by, so the stress evolves, and then we hit this black line first, which means that we would have a fracture at the injection point. So we actually did a simulation of this, and then we did indeed see fracture at injection point like this. But if the Biot coefficient difference is greater, if it's 0.8, so we start from here, and then we hit the failure line at the weak interface first. And in this case, we get the fracture at weak interface, not at the injection point. Okay, so we can repeat this exercise for different viscosity. So if we consider water viscosity that corresponds to a temperature of 360 degrees C, then these two lines shift in this way. And in this case, for both cases of Biot coefficient difference, we hit the failure condition at weak interface. So in this case, we only expect remote fracture to happen. Okay. the condition for fracture at the injection point is only limited to this region. So the Biot coefficient difference has to be relatively small to expect fracture at the injection point. Okay, so that's the sort of analysis based on simple 1D poroelastic analysis. And we did hydraulic fracture simulation and trying to do a simulation of this Tohoku University's experiment, the hydraulic fracture experiment. And for the numerical method, we used the phase field model, and it is implemented in open source code, OpenGeosis. I will not talk about this numerical method today, but if you are interested, the source code is open. You can get it, and then also, yeah, there are some publications, so you can look at the numerical method. But instead, I just going to present the simulation results, what we got. So we have done these three cases. So the first case is at the low temperature. So the viscosity in this case is high. The water viscosity in this case is high. And we saw some, sorry, I forgot to explain what this is. So then in this simulation, we consider that this granite sample has some weak interfaces. So they correspond to grain boundaries. And at the grain boundaries, we assigned lower fracture toughness and also high Biot coefficient of 0.9. Okay, and then we inject fluid with certain viscosity from this borehole. Excuse me. In this first case, the fluid viscosity that corresponds to 200 degrees C. The water viscosity corresponds to 200 degrees C. And we saw this big fracture, big connected fracture. And as the temperature increases, we start seeing more isolated, small, complex fractures. And at high temperature of 400 degrees C case, we saw this small, isolated, remote fractures in this case. And in here, we plot the response of the pressures. And for 200 degrees C case, we see some, big pressure breakdown. But for high temperature case, so this blue is the high temperature case. We do not see this kind of pressure breakdown anymore. Instead, the pressure increases and then it kind of stays at high value. And indeed, in the experiment, they observed similarly. So for low temperature, they saw a big pressure breakdown. And as temperature increases, also in this 360-degree case, small pressure breakdown. And at the high temperature case, yeah, they did not observe almost no pressure breakdown. So yeah, so from this analysis, well, we can think that so the question to why fracture becomes complex, and we think there are two ingredients that we need. So the first one is that the rock has to be heterogeneous, and heterogeneous in terms of Biot coefficient. So rocks such as granite, stiff rocks with some defects or some grain boundaries and so on. And also, injection fluid should have very low fluid viscosity. So from this analysis, we think that those two are the required ingredients. Okay. So then we did experiment, or our collaborators in Tohoku University run experiments. So for this experiment, we picked this rock sample called Akiyoshi marble. So we chose two two kinds of Akiyoshi marble, two kinds of marble. So one of the marbles have very fine grain. The other one has a very coarse grain. So this fine grain marble, we can think of this as homogeneous rocks. And coarse grain sample, there are lots of grain boundaries, and then we think of this as a heterogeneous rocks. So we have fine grain and coarse grain that represent homogeneous rocks and heterogeneous rocks. And for injection fluid, we chose water and CO2. So the experiment condition for them are not high temperature. So temperature is only 50 degrees C, and we apply confinement pressure of 30 megapascal. But this is enough for CO2 to become supercritical condition. So at this condition, water viscosity is this 5e minus 4 Pascal second, and CO2 viscosity is 1 order magnitude smaller, 3.5 e minus 5 Pascal second. So CO2 is already supercritical condition. Well, so as for experimental setup, the details are in this paper that I mentioned already. So this is the result from the fine grain marble or homogeneous sample. And when we use water or CO2, we saw similar fracture generation. So both cases, fractures look pretty much conventional, the bi-wing planar fractures. Okay. And for heterogeneous sample or coarse grain sample, when we inject water, we see this big fracture formation. But still, the propagation of fracture is very much impacted by the grain boundary. And when we inject CO2 or supercritical CO2, the patterns of fracture looks very different now. So we don't see, these big planar fractures anymore. These fractures are small and isolated, and also that the fractures do not initiate from the borehole. They somehow nucleate from at isolate location remotely from the borehole. Right. So yeah, so at the moment, our university, Montana University at Leoben and Tohoku University have a joint project called REMAIN, Remote Activation of Geological Interface. So then here, we are looking at the characteristic of the rocks. So when we have heterogeneity especially in the Biot coefficient, and also this supercritical or low viscous fluid seem to have impact on how fractures form when rock samples are heterogeneous. So one possible idea is that maybe we can change the fluid viscosity during hydraulic fracture operation, for example. So these small isolated fractures, so they seem to be induced by low viscous fluid injection, but if they are not connected with borehole, they do not contribute to the productivity, right? But if we inject low viscous fluid first, and then if we create these complex remote fractures first, and then if we switch to high viscous fluid like water, and then if we make a big fractures, and then we may be able to connect those isolated fractures, and then in this case we may have more complex fractures that are more effective for geothermal energy extraction, for example, in supercritical geothermal system. Yeah, so actually that's all I have today, and I'm happy to take any questions you might have.
Okay, well, thank you, Keita. We're open to questions. Let's go to the chat. Wenching has a question. He said, "Thanks for the great work. For your phase field hydraulic fracturing simulation, did you assign damage equal to 1 for pre-existing features? And how did you treat the permeability of those fissures?"
Mhm.
And let's just see. Did you model the thermal field explicitly, or were the temperatures only reflected by the varying viscosity?
Yeah, thank you for the questions. Yeah, so first for how we treated pre-existing fissures. So no, we did not assign phase field 1 or 0 in our case. But anyway, no, uh, those pre-existing features have no damage. They have low fracture toughness and higher Biot coefficient. So 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 physically we consider them as just a weak interface, not open fracture or not broken part. It's just the interface that has a less stiffness or less toughness.
Okay.
Yeah, and then another question. Yeah, the other question about the thermal. Yeah, so in this experiment or simulation, it's actually isothermal. So here, 200 degrees C, but the both the rocks and water are 200 degrees C. So um, there's no thermal effect. So the injection temperature is same as the sample temperature, the rock temperature. So in the simulation, actually, we only change we only use the viscosity that corresponds to the particular temperature.
Okay. Now,
Mhm.
and Wenching says thank
Mhm.
you.
Mhm.
And the next question is from Quan Guo, and Quan
Mhm.
was wondering, in the experiment on the coarse grain sample injected with
Mhm.
supercritical CO2,
Mhm. Mhm.
was the sample saturated with water before the
Mhm.
injection?
Mhm. Yeah, thank you for the question. Actually, they are dry sample. So no, it's not saturated. Um, in this experiment. Uh, but uh, um, but we have well, not we. They have performed experiment uh, in addition to this with saturated sample as well, and observations are almost identical.
So, Keita,
Hmm. Hmm.
I have a quick question.
Yeah. Hmm.
Yeah, I really liked your one-dimensional
Hmm.
demonstration,
Hmm.
but that was steady state. Are there any
Hmm.
implications if
Hmm.
you
Hmm.
consider transient effects?
Hmm.
Does the
Hmm.
fracture possibly start at the wellbore where under steady state it
Hmm.
would start at
Yeah.
a fracture?
Yeah. Thank you for the question. Yeah. Sorry, I did not explain clearly. Well, I kind of skipped. So so up to this point, actually, this is analytical results, um, and well, yeah, this up to this point, it's analytical. But when we created this heat map of the stress, we actually used 1D numerical solution because we wanted to consider the coupling effect and also the transient effect. So this has the flow rate in it, and then also we consider time. So the time it evolves from here. So this is the transient effect, and then so if we draw a line where the stress becomes tensile more than 6.5 megapascal, for example, right? And then so the y-axis is the time. So this is when we start, and then the stress evolves like that. And so some cases actually we do not see failure at injection point. So in this region, for example, we never hit the failure criteria. Or in this high temperature case. So if we yeah if our conditions start here and then even even if we even if we wait for a long time or until the steady state, um, we do not see any failure at the injection point, right?
Okay, thank you.
John, I have a question, if I might ask.
Sid, you're hard to hear. You'll have to speak up.
Okay. I have a question.
Mhm.
Is your injection rate, that is, when you're pressurizing the borehole, do you
Mhm.
do that quite slowly? That is, quite slow buildup of pressure?
Um, well,
That is, as you inject
uh-huh.
fluid into the borehole,
Yeah,
do you build up the pressure in the borehole quite slow?
right. So for this 1D case, um, the injection rate, so well, we we actually did several different injection rates. Uh, I mean, from slow to high injection rate. But once we uh, non-dimensionalize it, the so- the
How slow
yeah.
is it though? Is it in
Mhm.
minutes or seconds or slower than that even? So how fast do you build up pressure in that borehole?
Yeah. So once we non-dimensionalize it,
No, no,
this
never mind the
yeah,
non-dimensional.
it doesn't. Yeah.
Physically, just physically, how fast do you build up? Is it in seconds or is it in minutes?
Okay, so this 1D bar is it's does not represent. I have to I have to look at the paper. How what's the actual injection rate? So it's written in this paper, but this sample itself is well you know we normalize everything. Uh, um, yeah, sorry,
See,
I don't know. Yeah.
I
Hmm.
think it was very
Hmm.
nice work, a
Hmm.
very nice
Hmm.
job, and I compliment you on this very nice work and going to high temperatures is very good.
Hmm.
However, if you're building
Hmm.
up pressure slowly,
Hmm.
you're actually
Hmm.
injecting into the granite, even though the granite's
Hmm.
impermeable, you're
Hmm.
still injecting into that granite as opposed to if you build up pressure more rapidly,
Hmm.
where you might tend then to get a simply a through-going fracture that
Hmm.
once it initiates at the borehole, then it jumps right through.
Hmm. Hmm.
So the
Yeah,
Hmm.
question is whether these effects are due to simply the injection of fluid
Hmm.
because you're building up pressure slowly,
Hmm.
and therefore the viscosity of the fluid would be key, as you say. It's
Hmm.
very nice work you did.
Hmm.
yeah, I agree. It's a very, very nice work. I'm following up on my question on the sample saturation.
Hmm.
If the sample were saturated with the water and then
Hmm.
displaced with the supercritical CO2,
Hmm. Hmm.
won't you have displace a higher viscosity fluid with a low
Hmm.
viscosity fluid? So you
Hmm.
have a fingering effect?
Hmm. Hmm.
Yeah.
Um.
Because this could
Hmm.
also, promote
Hmm.
more
Hmm.
inhomogeneous, like a fracture
Hmm.
random creation.
Yeah.
And
Yeah.
it have
Hmm.
a
Hmm.
super, very,
Hmm.
very critical application
Hmm.
for CO2
Hmm.
sequestration because
Yeah. Hmm.
usually you inject into a saline, formation. Yeah.
Yeah, yeah, I agree about the CO2 fingering, but this in this experiment sample is very small, so we did even with a saturated sample, it's just the length is not enough to see any fingering in this this instability So yeah, but for the field scale for if it's like hundreds of meters, and then yes, um, this fingering should happen at some distance.
How big is
Yeah.
the sample anyway? I mean, this go back to what Sid's question two. What the injection rate? How big the sample? How big is the borehole?
So the sample is very small. So okay, I don't want to give you the okay, like a few centimeters in diameter.
Okay, thanks.
Yeah. Yeah,
Thank you.
yeah, I have to look at this paper for the exact size, but it's very small, like this much.
Well,
Mhm.
we're out of questions. And any last words, Keita?
Well, no, but yeah. So yeah, I think this this complex structure with CO2 injection or low viscous fluid injection is not new. I mean, it has been observed by many people in many experiments, and then yeah, and then I think that well, I hope we offer a plausible explanation why this happens, and then we believe that this happens when we have the right condition of where, if we have a heterogeneous rock formation and also low fluid viscosity. So when we have these two conditions, you know, I think we can happen. And also, I would very much like to see, you know, someone to try, this in a bigger scale outside of the laboratory in the field, possibly to, alternate or change the fluid viscosity from low to high to see, if you can achieve more complex structures. Yeah. So yeah, that's my that's my last wish.
Oh, well, your best wish, anyways.
Yeah.
So just for one member of the audience, Professor Kim, in a few words, can you just summarize once again why the fracture does not propagate from the borehole?
Ah, so so okay, so if the fluid viscosity is very, very low, you cannot just generate enough pressure, right? So if the fluid viscosity is very, very low, you cannot create enough pressure at the injection point. So that's why the fracture will not initiate out of the borehole, but if you have some weak interface away from the borehole, even though fracture will not initiate out of the borehole, the weak interface here, the Biot coefficient is high, or 1. And for high Biot coefficient, the fluid pressure impacts more at high Biot coefficient rock. And even though fluid viscosity is too low to induce fracture at the injection point, it may be enough to induce fracture at weak interface. So in this situation, you will not have fracture not at the injection point, but at a distance at weak interface.
Very good. And that was clear.
Yeah, thank you.
And we have Thomas Finkbeiner is saying he enjoyed the presentation, and Thomas is wondering if the recording is going to be available. Yes, this recording will be posted on ARMA's website. There's a tab for the Hydraulic Fracturing Technical Committee, and under that, all of the seminars, or the ones that we can record, are posted. So with that,
this is Kate Baker. I have
Kate.
a comment.
Please.
Yeah, I am just harking back to the Huff and Puff special meeting that we had, and wondering what would happen if you introduce a surfactant into this. Is wettability going to be important?
Oof.
And is the certainly in a carbonate, the wettability of carbonate to CO2 and to water is very different.
Well, yeah, thank you for the question, but to be honest, I don't know. So we have not looked at capillary pressure or multi-phase flow in our analysis. So I cannot answer the question.
I just think it would be interesting for field trials to see what would happen there.
Yeah, certainly. Yeah.
So Kate, would you like to speculate?
Yeah, okay.
Well, either one of you.
It might affect the fingering, but I don't know. But beyond that, I can't pull up either a mental image or a mathematical model.
Okay.
Yeah. Well, then let me just guess that it will help.
Okay. Well, we can end on that note. That it probably has value. But tremendously interesting presentation, and I think it could potentially explain some really important observations and have some real application.
Yeah.
So I'd like to thank you sincerely for the presentation, and thank everybody for joining in.
Yeah, thank you very much.
Thank you all.
Thank you. Bye-bye.
Right.
No, fascinating. Really, as I said, I really enjoyed your one-dimensional analog. I mean, that I hadn't thought along those lines before.
Yeah, thank you very much. Yeah, so it started first we are just running the simulations, and then we saw some strange cases, like sometimes fracture does not initiate out of the borehole. And then, first we thought we made some mistake, and then
if you inject long enough, will it grow back to the borehole?
No, it will not. So
really,
so for when the fluid viscosity is just too low, you cannot generate. You cannot just generate enough pressure at the injection point. But sometimes, like if you set some weak interface, then we saw that the fracture pops up at the weak interface, and then first we saw it in the simulation, and then from numerical simulation we thought we made some mistakes. Then we just try to solve it analytically in 1D. 1D we can solve it analytically, and then we found that certain cases actually indeed the tensile strength at the remote interface is actually greater than the tensile strength, tensile stress at the injection point, and then
very eye-opening.
Yeah. Well, thank you very much.
Hey, and we have a place for you in 2 years or sooner, if you want.
Yes. Hopefully.
It might not be me. It might not be me, but this was awesome. I mean, really kind of thought-provoking, and people don't think about this.
Yeah. So, thank you very much for this opportunity. Yes.
Yeah. Thanks, man.
Okay. Thanks. Yeah.
All right.
Okay. Then. Yeah. See you. Yeah. Hopefully in China.
Yeah. For sure.
Yeah. Yeah.
Okay.
Yeah. Then have a good day.
Bye-bye.
Yeah. Bye.